You know, there's this hidden world, this invisible infrastructure that makes pretty much everything you do online even possible. Today, we're going to pull back the curtain on the real magic behind the internet, the invisible superhighway, and how it is all powered by pure light.
Seriously, just think about that for a second. A live stream, a video call with someone on the complete other side of the planet, and it just shows up almost instantly. I mean, how is that even possible? It absolutely feels like magic, but it's actually one of the greatest engineering feats in all of human history.
Now, you probably think the answer is just, the cloud, right? Some sort of abstract thing floating up in the air. But the reality is way more tangible, and honestly, it's a lot cooler. The answer isn't up in the sky. It's buried under our feet and stretched across the ocean floor in a massive global network made of pure glass. Okay, let's dive right in. To really get this network, we've got to follow one single piece of data on its incredible journey. And it all kicks off with this really fundamental transformation, turning our digital clicks into actual beams of light.
So the moment you hit send or click play, your data starts out as simple electrical signals. It travels out of your local network to a facility that's basically the main on-ramp to the internet's backbone. And this is where something incredible happens. Super powerful lasers take those electrical signals and convert them into these incredibly fast pulses of light, getting them ready for a seriously long-distance trip.
All right, so our data is now light, but what is it actually traveling through? Let's take a closer look at the physical road itself, the glass superhighway.
This highway is made of what we call fiber optic cable, and it's just beautifully simple. At its very heart is the core, a strand of pure glass that's actually thinner than a human hair. That's where the light zips along. Wrapped around that, you've got the cladding, which, well, that's the secret sauce. And then finally, there's an outer coating, which is just there for protection.
So how do that core and cladding work together? Well, the cladding is made of a slightly different kind of glass that acts like a perfect, flawless mirror. So when a pulse of light hits the edge of the core, instead of leaking out, it bounces perfectly back inside. This little bit of physics magic is called total internal reflection, and it's what allows light to just zigzag down this tiny glass tube for thousands of kilometers without ever escaping.
And this gets to the absolute heart of it. The key phrase is right here. This allows the light to travel long distances with very low loss. See, unlike electricity in a copper wire, which loses energy as heat, these light pulses are just breathtakingly efficient. They hold their shape and their power over these enormous distances.
And just like real highways, you've got different types for different trips. For the long-haul internet backbone, we're talking those massive undersea cables. They use something called single-mode fiber. It has this teeny-tiny core that keeps the light signal pure and lets it go for thousands of kilometers. For shorter hops, like inside an office building, they'll use multi-mode fiber. But for the global journey we're talking about, it is all about that long-distance champion single mode.
Okay, so we've got a super efficient highway. But how on earth do we fit an unbelievable amount of traffic onto it? Well, that brings us to our next section, and a concept that is just as beautiful as it is powerful: packing data, by creating lanes with rainbows.
The whole idea here is so simple, it's brilliant. If one single fiber optic cable is a single-lane highway, how do you upgrade it to handle more traffic? You don't have to build a whole new highway. Nope. Instead, using a technology called DWDM, you create dozens of invisible lanes on that exact same strand of glass.
And here's the technical name: dense wavelength division multiplexing. I know it's a mouthful, but all it really means is that we send a whole bunch of different data streams down the same fiber, all at the same time, by making each one a slightly different color of light. Wavelength is really just the scientific word for color.
And here's how it works. At the beginning of the journey, you've got a device called a multiplexer, or just MUX. It takes all the different light channels, your reds, your greens, your blues, and combines them into one single fiber. That combined beam of light travels across the country, maybe even an ocean, and then on the other side, a demultiplexer, or DMUX, does the exact opposite. It separates all those colors back out perfectly to their own individual destinations.
So what kind of capacity are we actually talking about here? With this DWDM technology, a single strand of glass can carry, wait for it, 8 terabits per second.
Okay, let me try to put that number into perspective for you. 8 terabits per second. That is enough bandwidth to stream over 1 million high-definition movies simultaneously, all through one single strand of glass thinner than a human hair. I mean, the scale of that is just mind-blowing. So we've got this massive multi-lane superhighway just packed to the gills with data. But all that traffic has to take the right exit, right? So how do you direct all of this light? That's where we're going to get into next, how to take the right exit on this highway of light. The absolute key to managing traffic that's moving at the speed of light is to, well, keep it as light. This is called optical switching. The entire goal here is to route the light from an incoming fiber to the correct outgoing fiber without ever stopping to convert it back into a slower electrical signal.
And the advantage is just so clear when you see it like this. The old way, electronic switching, was this messy bottleneck. You had to convert light to electricity, sort it all out, then convert it back to light again. It was just slow. New optical switching keeps everything as light. It's clean, it's elegant, and it is massively faster, which allows it to handle that enormous bandwidth that DWDM provides.
And how they do it? Honestly, this is straight out of science fiction. Inside these optical switches are these arrays of thousands of microscopic mirrors. And these tiny mirrors can pivot with just incredible precision to physically catch a beam of light coming from one fiber and bounce it perfectly into another one. We are literally directing the internet's traffic by moving tiny little mirrors. It's amazing. This whole system is an absolute engineering marvel. But of course, it's not without its challenges. So for our final section, let's just zoom out and look at the big picture trade-off here. Speed versus complexity.
And this table lays it out pretty clearly. On the one hand, the benefits are world-changing. You've got this huge capacity, incredible long-distance reach, and it's totally scalable. But on the flip side, this stuff is not easy. The equipment, the lasers, the switches, the amplifiers, it is very, very expensive. Designing these networks is incredibly complex. And when you pack that many colors of light that close together, you've got to worry about them interfering with each other or the signal getting distorted.
But when you boil it all down, the entire philosophy of this whole global network comes back to one simple, elegant goal: maximize the distance your data can travel as pure, unadulterated light. Every single piece of technology we've talked about today serves that one single purpose.
And look, we're not just talking about a few cables here. This is a vast, interconnected global web. Every single node on this network, every trunk line connecting continents under the sea, it all relies on these very same principles to connect billions of us instantly.
So the next time you stream a video from halfway across the world, just take a second to remember this invisible superhighway. It is the true physical foundation of our modern digital world. But that does leave us with one final fascinating question to think about. What happens when our ever-growing demand for data starts to push the absolute limits of the speed of light itself?